review some terminology. Elements. You should know these definitions because there might be a paper 2 question where one part of the question is asking for a specific definition. So knowing how IB defines these things might be helpful. Who knows? I don't know what the questions are going to be on the test, so but I've seen somewhat obscure definitions end up on there. Yes?
Would we later need to go over past tests?
Yes, absolutely. I will be giving you out full past former tests. Now, recognize that last May was the first time they did the new curriculum. So that will be probably, my plan was to give that to you guys as a mock test, okay? So closer to the time, but I will happily give you full practice tests if anyone wants to do that like on a weekend. I know some people have a lot of stuff going on weekends. I'm here almost every Sunday morning because there's a church here, the building's open, so so if people want to just come in and be like, what is it like to take an entire test or even just an entire paper 1A, we can absolutely do that. I have a whole file drawer of old tests, so yeah. And of course the question bank questions that I give you on quizzes are from old tests, but yeah, just having them organized like that can be really helpful. Good question. Okay, so element is a pure substance that cannot be broken down by chemical means. Okay, so yes, you can split an atom. You can, have nuclear decay happen or something like that, but a chemical reaction is not going to change what element it is. Okay. Compounds, 2 or more elements, chemically joined, so chemically bonded in some way. Could be an ionic bond, could be a covalent bond, in a fixed ratio. So always the same ratio of the 2 different elements together. So Cl2 in this case, not a compound. It is a molecule because there's 2 atoms, but it's not a compound because there's only 1 element. Okay, so that still counts as an element. Okay. Compounds have different properties from the elements, right? Sodium explodes in water, chlorine, very toxic gas, sodium chloride, delicious, okay? Yeah, just table salt. Yeah. Okay, so we're kind of, I had you guys diagram this out last year, but we're kind of moving from the pure substances, which are elements and compounds, over to the mixtures side of things. More than 1 element or compound that are not chemically bonded together, okay? And there's always, with like dissolving ionic compounds and things like that, there's always a little bit of a gray area, but pretty much if you can separate a mixture by physical means, not doing a chemical reaction, then it's considered a mixture and not a pure substance. If you have to do a chemical reaction in order to separate out the parts, then it's a compound. Okay? They retain their individual properties, but again, when you get into things like dissolving salt in water, the sodium and the chloride ions separate and dissolve, right? They get solvated, and now the whole mixture conducts electricity where the solid sodium chloride would not. So, their individual properties with a little wiggle room given the context, okay? But it's not like sodium and chlorine coming together to make table salt. We can have generally two types of mixtures. A homogeneous mixture is uniform, and typically our solutions, we talk about solutions as homogeneous mixtures, whether we're talking about a solution of gases like the air in this room, or a solution of solids like the brass in this key, or a solution of salt and water, liquids. Typically, if you can see through it, it's a solution if we're talking about liquids. Heterogeneous, visibly different substances or phases. So that could be sand and water, it could be oil and water. They separate into layers. It could be, yes, something like sand that's going to precipitate down. It could be a glass of water or a flask of water with a stopper on it, where there's a mixture of things in that flask, but there's a clear difference between the air and the water. We've done a little bit of this. We're gonna do more of this a little bit later. So probably when we are doing the organic reactions, I'd like us to practice some recrystallization and filtration. We're definitely gonna do a distillation lab. And I have to think about how I wanna do chromatography. But we'll look at these techniques, if nothing else, then in one of those lunch lab demo sessions. But these are ways that we can separate mixtures that do not involve a chemical reaction, right? So we can dissolve things. That's kind of making a mixture more than separating mixture. We can filter things. We can recrystallize something out of a solution. We can evaporate part of a solution. We can distill, separating two liquids. We can use chromatography to separate parts of a mixture and be able to see the individual parts. So these are just things that we can do, and you guys will get to see. I mean, you've seen Salvation a million times, but you'll get to see all of these a little bit later. All right, solid, liquid, gas. Okay. Shape, volume, compressibility, and fluidity for each of these. Understand that the particle diagrams, the solid is usually going to be shown as some sort of crystal structure or sort of rigid shape inside of a container. Liquid will usually be disordered, but particles touching each other. Gas is going to be particles not touching each other. Shape is, does it take the shape of its container? That's what we're asking with shape. So do solids take the shape of their container? No. Liquids? Yes. Gases? Yes. Right. Volume and compressibility are kind of the same thing. Not exactly. Fixed volume is going to be solid and liquid. Gas is not fixed, right? Gas is a variable volume. It'll expand to fill whatever container it's in. Compressibility is very high for gases, very low for liquids and solids. There's just not anywhere for the particles to get closer together. And fluidity, fluids are liquids and gases, not solids. But they both, we think about fluid as being almost like the same term as liquid, but a gas is also fluid. It flows. So, fill these in real quick for later. Oh no, it's doing the thing. Ugh. It hasn't done this yet all year. Okay, well, I'll fill this in later and post it before I post the slides. Depends, does this thing. State changes, we need to know what they are, what they're called, and what's happening with energy. So in this phase change, are we absorbing energy, or is the system releasing energy? So most of this we're pretty familiar with. The terms that you have to remind yourself to remember are sublimation, going from a solid to a gas, and deposition, going from a gas to a solid. That reminds me, I'm going to write myself a note to put together the iodine demo. It's a pretty simple demo that shows both sublimation and deposition. And also remembering, I think that the fact that it takes energy to melt something, I think, is very intuitive. But remembering that freezing something actually releases energy to the surroundings. It's sometimes hard to wrap your mind around that. If you struggle with that, think about sweating, right? We talked about this last year when condensation when sweat evaporates, we feel cooler, right? Because it took heat from our skin, right? When something condenses when water molecules condense on the outside of a cold glass on a hot day, it's actually giving warmth to the glass, in a sense, by condensing on the outside, okay? Or energy, anyway. So you're going to have to know all these terms. Feel free to do flashcards, whatever you need for that. I am not going to fill this out. You don't have to fill this out. There's not anything specific that you haven't heard 100 times for this. If you have questions about it, let me know. Or just look at, I will be posting the study guide and the answer key to the study guide in Canvas, so you can just get what he thinks are the answers there. State symbols. Every time on the IB exam that they want you to write an equation, then you are going to be expected to include state symbols. Okay? And we're going to talk as we go, especially with the organic stuff, about like, how do you know if it's going to be solid or liquid or gas or aqueous, right? And a lot of times that you'll have clues in the question, or they describe the reaction, or it will be a reaction that you will have been expected to have done in the lab. So metals are solid, right? This is generally we're assuming at room temperature, standard ambient temperature. Water's a liquid. Anything that is dissolved in the water is going to be aqueous. And the gases, certainly the molecular gases, you can see there in blue on the shower curtain. But just knowing, we'll talk more when we get into intermolecular forces about how do you know that something's going to be a gas, how do you predict that, versus a liquid versus a solid. Okay. Celsius and Kelvin. When we did gas laws and thermodynamics last year, we talked about this a lot. Sometimes you absolutely need to put things into absolute temperature, which is Kelvin, right? So we've talked about that quite a bit. I'm not going to go into detail here. I'm also not going to make you do these, although if you want to, you can. Notice that this says add or subtract 273. If you look in the data booklet, it says 273.15 degrees Celsius is, Kelvin is 0 degrees Celsius, okay? I think the 0.15 doesn't matter. I don't think they care if you use the 0.15 or if you don't use the 0.15. The 273 matters, but it's in your data booklet and you're going to have your data booklet for any questions, right? And last thing is heating. Well, I'll let you guys take a look at this and let me give you your, real quick, let me give you your homework. That's not it. Where did I put it? It's right here. Sorry, that clock's a little bit off. Textbook's still up for checkout at the end of the day if you want.